Hello, this time I will discuss about Field-Oriented Control, or FOC, starting from its explanation to its implementation on STM32. In a BLDC motor, for smooth rotation, a three-phase sinusoidal current is required. However, this current cannot be arbitrary. Its value must be controlled to always match the desired conditions. So, how do we control these three phases to produce the correct sinusoidal current? Do we need to provide a sinusoidal reference signal for each phase? Of course, that would be very tedious and inefficient. Fortunately, there's a solution called the Clarke and Park transformations. The Clarke transformation converts the current from three phases into two components on the stator axis, the alpha and beta axis. Next, the Park transformation rotates these axes to align with the rotor, producing two fixed components called the direct and quadrature currents. The D component aligns with the rotor's magnetic field, while the Q component is perpendicular to it. To generate torque, we only need to control the current on the Q axis, while the current on the D axis can be set to 0 or negative if using field weakening. This is the basic principle of field-oriented control. By controlling these two components using PI controllers, we can generate stable and precise three-phase sinusoidal currents without manually creating sine signals. The output of this control is converted back into three-phase voltage using the inverse Park transform and space vector PWM. Key hardware components for FOC include an inverter, current sensors, a rotor position sensor, and of course, a microcontroller. For this implementation, I used MDU 1512 MOSFETs and a DRV8302 gate driver as the inverter, configured in 6-mode PWM. The DRV8302 includes a differential amplifier for current sensing from shunt resistors and an internal buck converter to supply power to other components like the microcontroller. For rotor angle measurement, I used the AS5047 magnetic encoder via SPI communication. The microcontroller is an STM32F405. I also designed a custom PCB size for my DIY actuator project with a magnetic encoder placed at the center. A magnet is mounted on the motor shaft so that when the PCB is installed, the AS5047 can read the magnetic field and calculate the rotor angle. The software was developed using STM32 CubeMX and PlatformIO for flexibility in writing code with VS Code. The first step is to configure PWM using Timer 1, as this is an advanced timer that supports complementary PWM mode. In the PWM configuration, CHX and CHXN must be enabled to generate a 6 PWM signal. Do not forget to set the dead time to prevent a short circuit between the high side and low side MOSFETs. For switching efficiency, I use center-aligned PWM, where only one switching change occurs among the three pairs of MOSFETs in each cycle, thereby reducing switching loss. Since the method used is low-side current sensing, current readings are only valid when the low-side MOSFET is in the on state. Therefore, ADC readings need to be synchronized with PWM switching. STM32 supports this with the ADC trigger feature from the timer. Here, I use the update event as the ADC trigger. I also adjusted the I/O configuration for DRV8302, as well as the LED pin on PC13. ADC1 is used to read the current from two phases of the motor. The third phase is calculated using Kirchhoff's law. The mode used is injected conversion mode, so that it can be triggered by the timer. The channels used are channel 8 and channel 9. Don't forget to enable the ADC interrupt in the MVC settings. To read the rotor angle, SPI1 is used to communicate with the AS5047, and DMA is enabled to make angle reading faster and reduce CPU load. I also use the USB CDC feature for communication with the PC, such as monitoring motor signals and tuning control parameters. Therefore, an external crystal is required for USB to function. Additionally, I have enabled FreeRTOS for task management, as this system will evolve and become more complex in the future. Before starting to control the motor, the first step is to ensure that the board is working properly, usually by blinking the LED. After that, Activate the DRV8302 gate and try to generate a PWM signal without load. Make sure there is no short on the MOSFET. I have prepared several functions for configuring the DRV8302 and setting the PWM frequency. Here I'm using a frequency of 10 kHz, which is common for BLDC. If the inverter is safe, the motor is connected and supplied with a sinusoidal voltage in open-loop mode using the inverse part transform and SVPWM. The goal is to ensure that the PWM system, signal generation, and driver are functioning properly. The next important step is to read the rotor angle. According to the AS5047 datasheet, we need to send the command 3FFF so that the sensor returns the read angle value. After the sensor finishes sending data via SPI, the SPI callback is executed and the data is converted to degrees. However, it is important to note that this angle is relative. We do not yet know where the 0-degree position is relative to the stator. This is where we need to perform offset calibration. There are two types of angles that must be distinguished: mechanical angle and electrical angle. Mechanical angle is the physical position of the rotor relative to the motor body. Electrical angle is the angle between the stator's reference axis and the rotor's magnetic field axis, scaled by the number of pole pairs. The electrical angle repeats every pole pair. So if the motor has 7 pole pairs, one full rotation of the rotor results in 7 electrical angle rotations, or 2,520 electrical degrees. FOC operates in the electrical domain, so the mechanical rotor angle must be multiplied by the number of pole pairs to obtain the electrical angle. For offset calibration, the rotor is locked in one direction by applying a current vector to the D-axis only. The rotor will align with the direction of the stator's magnetic field. The sensor angle at that point is stored as the offset, and this value is subtracted from each subsequent angle reading to ensure accurate electrical angle measurements. To read the current, I created a callback function that is automatically called when the ADC finishes reading the data. Since the ADC trigger is synchronized with the timer, the current reading will always occur when the low-side MOSFET is on. The raw ADC value is converted to current and equipped with a low-pass filter to reduce noise. After that, the current from the two motor phases and the rotor angle are converted to D and Q currents using Clarke and Park transformations. The actual ID and IQ currents are compared to their reference values, then controlled using a PI controller to obtain the compensation voltage. This voltage is converted back to alpha-beta form, then sent to the SVPWM. Finally, we perform PI tuning. Since I am not very familiar with the mathematical calculations to obtain the KP and KI values, I use the trial and error method. I usually start with a small KP value, then gradually increase it until the current follows the reference quickly. After that, I add KI to eliminate steady-state error. I also created a GUI to simplify tuning, using USB CDC as the communication medium. This GUI can display motor response graphs and receive tuning parameter commands. In the future, these parameters can be stored in flash memory to remain saved even when the power supply is turned off. With the implementation of FOC, BLDC motors can be controlled smoothly and precisely. If you're interested, I have included the hardware designs and firmware in the description below. Thank you for watching.